Hello, and welcome to episode 4 of our nuclear physics series for grade 12 physics. Today we're going to be talking about the energy released by nuclear reactions. We've already looked at a couple of types of nuclear reactions, and we know that there's a lot of energy bound up in the nucleus of atoms, so whenever a nuclear reaction happens, there must be an energy change associated with it. So, let's take a look. In your class folder or in your class notebook, you'll actually see these examples that I'm going to be working through today. So if you want to take a look at them, you can go find them there. So here's the first example. For this one, we're going to be looking at the beta negative decay. There's a Greek letter beta, remember, the beta negative decay of thorium-234. You can see that it starts as thorium-234 and turns into proactinium-91. And it emits an electron and an antineutrino. Now, I've already written down the masses here. These masses I found from our isotope mass table, which is in the class notebook as well. I also found the electron from our formula sheet. So if I look on our class formula sheet here, you can see the mass of an electron in atomic mass units that I've found. Now, when I'm looking at this in atomic mass units, one thing to note is that an atomic mass unit is often a more reasonable number to deal with than kilograms. If I look at the mass in kilograms, I have lots of scientific notation. Atomic mass units is a little bit easier to deal with, and it also provides a nice comparison between the mass of a proton and the mass of an electron. You can see the mass of an electron is very, very small, and the mass of a proton is much more reasonable. So, a couple of things to note. One thing is one atomic mass unit, so one U, or AMU it's also called as well, atomic mass unit, is equal to 1/12 the mass of carbon-12. So carbon-12 has an atomic mass of exactly 12. 6 protons, 6 neutrons. When we figure out the mass of the protons and neutrons, we can calculate that in AMU, and everything else is based on there. There's also conversion factors. One atomic mass unit is 1.66 and a bunch times 10 to the negative 27 kilograms. And we can also talk about one atomic mass unit in terms of MeV. So this here is an important conversion factor. If I'm looking at one atomic mass unit, that is a 931.5 million electron volts. That is an important conversion factor that we will use a lot in this unit. So, to start off with, remember that energy must be conserved. From our mechanics unit, we talked about work and energy. Energy must be conserved no matter what form it's in, whether it's in potential energy or kinetic energy or nuclear binding energy or any other form of energy, it must be conserved. So what we're looking at here is just like for mass defect and binding energy, we're looking for how much did the mass change, and we're looking for that missing mass. So with our reaction here, I'm going to figure out everything that was before the reaction happened, so before, and then everything after, and I'm going to find the missing mass. So I've already written these down. Beforehand, I have my thorium-234 mass, so that's 234.043601. That's my mass before. To find my mass afterwards, I need to take my proactinium-234 and my electron and add them up. So I'm going to subtract those masses. So I have 234.042895. And I'm going to add in the mass of the electron, which is 0.00054,858 atomic mass units. And I found that from my formula sheet there. So I have, this is the before, and this is the after, and that is going to get me my change in mass, or my missing mass here. So to find that out, I do that on my calculator, and I get 0.0001572 atomic mass units. So this here is the amount of missing mass. Now, one thing to note, in my reaction here, I do have an electron neutrino, which I kind of ignored the mass of. The reason for that is I went and looked up the mass of an electron neutrino, and if you notice, it's kind of ridiculous. It's about 2 × 10⁹ atomic mass units, because we're not very certain of the mass of neutrinos. And if I actually look here, that is past the number of decimal places I've got here. So the precision that we were able to measure the mass of thorium, peractinium, and the electron here does not account for the mass of this neutrino. That mass is too small. So if we're looking at our significant figures, the mass of the neutrino is just insignificant. So I can effectively ignore it for this case. I can pretend that this neutrino is massless for the case of this, and it won't affect my answer. If you go on to do nuclear physics in university, please ignore that I just said that. So here's the idea. This missing mass here is in atomic mass units. Just like before, I want to convert this missing mass into energy. If I was going to go from kilograms to joules, I would use E = mc². If I'm going from kilograms to joules, I would use E = mc². However, I don't have kilograms and I'm not going to joules, so I'm going to use a different conversion factor. If I'm going from atomic mass units to MeV, I use E = m times 931.5, because that's my conversion factor here. And in fact, if I go back and look at my formula tree here, or formula sheet here, you can see that I've got both conversion factors on my formula tree here. This is for kilograms to joules. This is for atomic mass units to MeV. Both of those are useful. So converting this here, I'm going to go, my energy is 0.0001572 times 931.5. And calculating that gets me my energy released by this reaction is 0.1466373 MeV. So in this case, I have 0.147, rounded off, million electron volts of energy released by this reaction. Now, the interesting thing about this is that is very small compared to the binding energy in either of these two nuclei here. If I look at the binding energy of these nuclei, I have a lot more binding energy in there than in this, than is released by this reaction. But this is still quite a lot of energy, considering that this is only one reaction. So here I've got approximately 147,000 electron volts of energy. In comparison, most chemical reactions release energy on the order of single electron volts or tens of electron volts. So this is many times more energy than is released by chemical reactions. So the question then is, where does this energy go? And we can calculate this released energy here. We can also figure out that this released energy typically goes into two forms. The first major form this goes into is this excites the nucleus. So this proactinium-234 nucleus will likely be excited after this reaction, and then it might undergo further gamma decay. The other thing is this energy here is also often released as kinetic energy for the particles of the result as a result of this reaction. So a lot of that energy might be released as the kinetic energy of this electron, which we can then calculate using our kinetic energy formula or force times distance to get our work. So our kinetic energy, remember, half mv squared, I can figure that out. I can figure out how fast that electron was going if all of this energy was transferred into kinetic energy. And it turns out really darn fast. So thank you for taking a look at episode 4 of our nuclear physics. Don't forget to like and subscribe. Have a great day, everyone.